Okay, so I have one student, so I'll start and then others will join. Okay, so welcome to the week 3 live interactive session on the course NPTEL NOC25 titled Fundamentals of Semiconductor Devices. Uh, the course instructor is Professor Digvijay Nath, and I'll be the TA for this live session. I'm a PhD student at IIT Kanpur. So the schedule for my sessions is every Sunday 3 p.m. to 5 p.m. Let's quickly go through the guidelines. So in case you have any query, you can just raise your hand or you can ask it in the chat window. Please ensure that your microphones are muted when you don't intend to speak, and I'll appreciate your cooperation to make this an interactive session. Uh, please try to join a live session. I'm telling this to those students that are watching this in recorded form and have not attended the session. This session would be interactive only if you join this live, right? And I'm supposed to have student interaction in these sessions, which I'll not have unless you join this session. So please ensure that you join. Uh, so please keep pen and paper handy along with a calculator. The session recording link and the lecture notes will be shared by NPTEL course team. The prerequisites include the last week's lectures, which covered the following topics: the carrier scattering and mobility, low field and high field transport, introduction to diffusion, drift diffusion and trap statistics, current continuity equation, and the introduction to PN junction. So, does anyone have any doubt or doubts regarding these topics? Okay, I'll take that as a no and proceed to the first question. Okay,
Sir,
so
some
yeah,
assignment, weekly assignment, some question has
please come again. Please come again.
uh, weekly on assignment question number 2 and 8.
Assignment question. I mean, which assignment are you talking about? Are you talking about the assignment, the problems that I showed, or the which?
Weekly assignment.
I'm not getting. Can you type your query in the chat? Do you want me to go through assignment problem, week 2 assignment that you were assigned?
Yes, sir, I have a problem. I have a doubt,
Which
sir.
assignment? Which assignment? Is it assignment 1, 2, or 3?
Weekly on, sir.
Assignment 1, week 1.
Week 1.
Okay,
Question number 2 and 8.
that would probably divert this session. Do one thing, mail me the doubt that you have corresponding to that question, and I'll try to answer that. Okay, is that fine? Or if we get time towards the end of the session, we can probably discuss your doubt. It would be better if you had your doubt ready. You could present your screen, and that way I would have been able to address it more quickly. We'll see what we'll do. Do mail me your doubt regarding the question that you are talking about, uh, corresponding to week 1 assignment. So now let's start with the first problem, which is as follows. Just a second. Just a second. ये चाहिए तो फिर मैं ये सॉरी Sorry for the interruption. Okay, so this is our first problem for today's live session, which is as follows. So assume that in a given semiconductor, there is only one scattering mechanism present with a relaxation time of zero point 0.2 picoseconds. Okay. Uh, you need to determine the electron mobility in the sample. Now, if there were another scattering mechanism present with a relaxation time of zero point 0.3 picoseconds, you need to determine its solo effect on the electron mobility. Okay, and then what is the overall electron mobility in the sample if both the scattering events were present simultaneously? Okay, assume that your Mn star effective mass of electrons is 0.5 m naught, where m naught is the rest mass of electrons. Okay, so does anyone wish to answer how should we approach this question? No? Then I guess I'll proceed and show. So now your mu1 is equal to, first of all, wait, do you guys recall this formula? Mobility is your q tau by mn star. I'm assuming you were taught this in one of the lectures in this course. So now,
ahead, right? So this how
can you
electrons are
please mute your
and how
microphone?
electrons or holes are scattered by ionized impurity is very important because that will
Thank you. Okay. So now your this tau is your relaxation time, right? So now firstly we'll compute this mobility corresponding to your one scattering mechanism, right? There are two scattering mechanisms of interest, at least in this question, right? Your one scattering mechanism has got a relaxation time of zero point 0.2 picoseconds, right? So now we have tau 1 of zero point 0.2 picoseconds, right? So your mu1 would be your q tau 1 by mn star, right? So can anyone compute this for me? Put in the numbers. Q would be 1.6 into 10 to the power minus 19 coulombs. Your tau 1 is zero point 0.2 picoseconds, right? So it would be zero point 0.2 into 10 to the power minus 12. Then it's mn star. What is mn star equal to? 0.5 times m naught, right? So I'll write 0.5 times. What is the rest mass of electrons? Please try to answer the questions. Okay. So this is 9.1 into 10 to the power minus 31. Okay. So now I'm assuming you guys have calculator in front of you. Calculate this and let me know what is the value of the mobility. You can either directly unmute and answer it, or you can type it in the chat. Fine, either. No answer. This means you don't have a calculator with you. Please try to ensure that you guys have calculator with you next time onwards. So if you plug in the numbers, this comes
Why
about.
not 7?
Yeah, please. 7.
Why not 7?
5 point.
Why not 7?
Uh, can you type it in the chat? Just table it. Let me write what I got. It's 7.033 into 10 to the power minus 2 meter square per volt second. Is this what you were trying to convey?
So I'm getting point not 7.
Point, I'm just not getting your first digit. What is that? 0.7 I'm able to get.
Yeah. 0.7.
0.7. Okay. Okay.
Yeah.
So you might be getting 0.7 into 10 to the power minus 1. Is that?
Minus 31, and when it comes from the denominator, it becomes 31. So minus 31 is cancelling, no?
Yeah. Yeah. Minus 31 and minus 31 is canceling out. And then you are left
So
with
1.6
1.6 times
into
0.2,
0.2
which
divided by
is, yeah, 1.6 times 0.8 whole divided by 0.5 times 9.1. That was effectively what you were supposed to calculate.
Yeah, that's what I got it as point not 7.
Okay. So wait. Let me do that again on calculator. So if we write 1.6 times 0.2, 0.5 times 9.1. Yeah. Correct. I mean, effectively, this is same, right? See, what you wrote in the chat is 0.0703, right? This is what you wrote in the chat. Do you agree? You got this? I mean, I did it on calculator and I got this answer, 0.07032. Fine. And we can express this as 7.03 into 10 to the power minus 2. That is what I wrote. So both are same, okay? Okay. Now, since we express mobility in terms of centimeter square per volt second, so if we'll do the unit conversion, what is the answer that you'll get? It should be mu1 in terms of centimeter square per volt second. Either answer it on mic or just write it in the chat. So what you need to do is you need to convert meter square into centimeter square. Okay, someone is typing. Yeah, 10 to the power minus 4. And see, your 1 meter is 10 to the power 2 centimeter, right? So meter square would be 10 to the power 4 centimeter square, isn't it? So there would be a 10 to the power 4 factor from here, which would make it 10 to the power 2. So we'll be having 703.3, right? That is the answer. Okay. Is this clear? Write yes in the chat if you are understanding this problem. Okay, fine. Thank you. So now this was corresponding to your suppose scattering. This is scattering mechanism 1, right? But in the question, then we also have another scattering mechanism. Okay, I'll name that as scattering mechanism 2. So now let's compute the mobility corresponding to that. Firstly, we need to find the solo effect on mobility. How will we determine that? By treating it as an independent event, right? If you treat that as an independent event, what will be mu2? Your mu2 would be simple, right? Q tau 2 by mn star, right? What is your relaxation time for the second scattering event? It's 0.3 picoseconds, right? So your tau 2 is 0.3 picoseconds. Can someone quickly compute what is the numerical value of mu2? Just replace this by 0.3. That's it. What is mu2? Give me the answer in centimeter square per volt second. Okay, so you'll do this unit conversion as well. That way I'll get to know. Okay, someone did answer it, but do the unit conversion as well. Okay, you probably answered it in meter square per volt second. Right. So, right. Okay. So the student has answered it in the chat, and answer is 1054.9. Right. Yeah, it's 94. I'm taking it only up to first decimal place. So this is what you'll get as an answer. Now, the second part of the question, right? What is the overall electron mobility in the sample if both of your scattering events were present simultaneously? So, which rule do we use when multiple scattering events occur to compute the overall effect? Please interact and answer the questions. Otherwise, this session will finish within 1 hour. Again, I'm requesting to the students who don't attend the live session and watch it in the recorded form to please attend it from the next time. Okay, since I did not get any answer, I'll answer it myself. So your mu would be, I should say 1 by mu would be 1 by mu1 plus 1 by mu2, right? You have mu1, you have mu2. What would be mu then? Can anyone do it quickly for me? So this would be mu1, mu2 by mu1 plus mu, right? I mean, if you do the algebra, this is what your mu net would be, right? Net. So what is this mu net? What is this? Take out your calculator and do the calculation. Now only one student is answering the questions, or I guess one or two students. What about the other two? I want answers from them as well. This is just a plug and play question, right? Just need to plug in the values and answer the questions. Okay, so I got two answers. The first one is 421.98 and the other answer is 2.369. Why are these answers so different? Let me do one thing. Uh, the other two students that are present, which answer is right? - 2.369 is not correct, actually. Okay, I got one more vote for the same answer, right? 421.98. So the student which answered it as 2.369, uh, can you just recheck the calculation and see if you also get the same answer? Okay, so this is what we will get. We'll get the answer as 421.98. And what are the units? Units are important, right? I mean, what are the units? Quickly, you can even unmute it and answer it quickly. What are the units of mobility that you used to answer this question? Centimeter square per volt second. Good. This is centimeter square per volt second. So this was one way of solving this second part, the part in which both the scattering events were considered. The other method to approach this problem would be to first compute net relaxation time. And how would you compute the net relaxation time? You can compute that by using this formula. Your 1 by tau is 1 by tau 1 plus 1 by tau 2, right? Let this be tau net, right? This is your mu net. And then you can write that your mu net is equal to q tau net by mn star. I did not take the inverse. Okay. So that's why probably you got 2.369. Fine. So mu net is q tau net by mn star. Fine. So Convince yourself. If you'll approach it in this fashion, you'll get the same answer. What are the values of tau 1 and tau 2 that you'll use in this formula? Your tau 1 would be this, your tau 2 would be this. You'll use this formula and you'll compute tau net. You'll use this tau net here and compute mu net, and you should get the same answer. Okay, so that is the other method of solving this question. Is this question clear? Any doubts? Okay, I'll take that as a no. No one has any doubt. So we'll move on to the next question. So assume a bulk N-type semiconductor with your mobility as 1000 centimeters square per volt second. If electric field is Ex and that is equal to 100 volt per centimeter, what is the sign and numerical value of electron drift velocity? Does anyone uh, remember the relation of mobility and drift velocity in electric field? How are these three quantities related? This would have been taught in the course as well. Someone quickly answer it. How is your mobility, electric field, and drift velocity related? Unmute and let me know.
So the drift velocity is mobility times electric fields.
Correct. And now we are talking about an N-type semiconductor, okay? And we have mu n, electron mobility as 1000 centimeter square per volt second, right? Your electric field is given. So what should be the sign? I mean, the formula that you gave was scalar formula, right? I'm now asking a vector, corresponding vector formula for that in case of an N-type semiconductor.
Negative, sir.
Would it be negative? Why? The answer is correct, but I just need an explanation. Why?
Because N type, sir. N type, sir.
Yeah, it was N-type, but still, why the negative sign? Because
The
the
movement of
motion of the
electrons is opposite to the electric field.
electric field, correct. Thanks, Pranav. Okay, so this is the formula of interest for us, right? Mu n Ex. Okay, so quickly, although this is not asking the question, but had we been asked about a p-type semiconductor, right? What would be Vp, drift velocity for holes?
Plus mu p into Ex.
Yeah, mu px, right? There, because holes move in the direction of the electric field. So now we know this part, right? The sign will be negative, right? Because both mu n and Ex are positive, right? Had Ex been negative, then Vn would have been positive, right? Because the idea is your Vn and Ex won't have same sign because mu n would always be positive. Okay, so now your Vn is minus mu n is 1000 times 100. Okay, so let's do a unit calculation side. This is centimeter square per volt second multiplied by volt per centimeter, right? So this volt and volt would go, the centimeter and centimeter would go, and we'll be left with what? We'll be left with centimeter per second, right? centimeter. Yeah, centimeter per second. You missed out this second. Okay. So this is what is the required answer. Okay, this was pretty straightforward actually. Now let's take up a more involved question, which is as follows. Your p-type silicon sample with doping Na equal to 10 to the power 15 per centimeter cube is illuminated by steady light, and thus it creates an optical generation rate of 10 to the power 12 EHP per centimeter cube millisecond. Assume that it's 100% ionization. There is no trapping, and your uh, what these tau n and tau p are 5 microseconds. So what you need to determine your electron and hole concentration respectively, and what is the percent change from their equilibrium concentrations. Let's approach this problem step by step. Okay. So what is the doping in the sample? I need someone with me on mic that could answer it. Or you, all of you can chip in. What is the doping in the
10 power
sample?
15.
10 to the power 15. And this is acceptor ion doping, right? And since we are assuming 100% ionization, right? This doping would lead to what? Would it lead to holes or would it lead to electrons?
Electrons, acceptors.
Acceptor ions lead to holes, right? When you want to make a sample p-type, you dope it with acceptor ions, right? And you thereby increase the sample's hole concentration, right? That is the idea, right? So this would lead to hole concentration. So what is the hole concentration? So the idea is I'm trying to compute equilibrium hole concentration first before computing the non-equilibrium concentration, okay? Because I need this percent change from the equilibrium concentration, okay? So what is the equilibrium concentration? Let me label that as P naught. Can someone answer me what is P naught? P naught would be simply Na, right? Which is equal to 10 to the power 15 per centimeter, right? So if you know P naught, do you know what is N naught then? What is N naught? Which formula would you use to compute N naught? I'm asking simple questions, so I do expect answers as well. What is N naught? Would be Ni square by P naught, right? Which is equal to 10 to the power 5 per centimeter cube. So now your equilibrium hole concentration is 10 to the power 15, and your equilibrium electron concentration is 10 to the power
Ni
5.
square by P naught.
Yeah, Ni square by P naught. So do one thing. For this question, use Ni 1.5 into 10 to the power 10 per centimeter cube. Right. Then you won't get this 10 to the power 5, right? This is corresponding to 10 to the power 10. If you use this 1.5 factor, what is the value that you would get? the value would be, I mean, this would be multiplied by 1.5 square, which is 2.25, right? Into 10 to the power 5 per centimeter cube. Yes. Now it's fine. So we computed equilibrium hole concentration and equilibrium electron concentration, right? Now there is no trapping, right? And your tau n and tau p are 5 microseconds, right? So what is the excess electron and hole concentration? We have been provided generation rate, right? And we need to compute what is the excess uh, carrier concentration, right? Am I audible?
Yes, sir.
Okay, thank you. So your delta P would be your generation rate. Let me optical generation rate, right? Let me I mean use this GOP for that. Your GOP times your tau P. Why did it got disconnected? Are you guys able to see the screen?
No, sir.
No, yeah, that's it. Don't know what happened. Not sure. Present it again. Now it's visible, right?
Yes, sir.
Fine, fine, fine. So this would be your excess hole concentration, right? Your optical generation rate, which is this multiplied by this tau p, right? So can you now compute what should be this delta p? Anyone? Compute this and this, delta p and delta n. This would also be GOP times tau n. Since they both are 5 microseconds, will have the same value, right? What is that value? Multiply this by this. Right? This would be your delta P, this would be your delta A. Now, what is the net electron concentration, right? This was then the concentration of the holes, the excess hole concentration, right? This was excess hole concentration. right? And likewise for this. So if you now are interested in computing the overall concentration of holes, that would be P naught, add them up, right? For electrons, same, N naught plus delta N, right? Now, uh, this is way less compared to this. So what should I write P as? I can ignore delta P, right? I can write it as P naught, which is 10 to the power 15 per centimeter cube. Similarly, for electrons, I can, which should I ignore though? In case of electrons, my N naught is very less compared to the excess electron concentration. So I would ignore N naught and I'll be left with delta N, which is 5 into 10 to the power 12 per centimeter cube. So now I need to, what is the quantity that I was supposed to compute? Okay, the electron and hole concentration percentage change from the equilibrium concentration. Fine. So this would be then, let's compute the percentage change in electrons first. This would be, it was, I mean, it has reached this. Initially, it was this. So you will get this n minus n naught whole divided by n naught. Right? Times 100%. That is the required quantity. If you plug in the values, you'll get, what do you get? 2.22 into 10 to the power 9%. Right. So the idea is the electron concentration has changed considerably from its equilibrium value. If you do the same for holes, you'll get P minus P naught by P naught times 100%, right? What is that equal to? Answer it quickly. What is P minus P naught? Anyone? This is 0%, right? Why? Because your P is equal to P naught. Right? This is your P naught, and this is your P. If you plug in the values, this is 0%. Right? So your minority carrier concentration, that is getting considerably changed by the optical generation rate, while the majority carrier concentration is hardly affected. Okay, so that finishes your part one. What about part two now? Comment on the magnitude of this product NP. What is NP equal to? Me pull in a page. Your NP would be equal to your 5 into 10 to the power 12, right? Why? Because this is 5 into 10 to the power 12 multiplied by this times 10 to the power 15. If you do that, the numerical value is 5 times 10 to the power 27, right? and this would be centimeter minus 6, right? Because both have per centimeter cube. They'll be multiplied and we'll get centimeter is per minus 6, right? So now this is considerably greater than your Ni square. What is Ni square? Your Ni square is square of Ni. Ni is 1.5 into 10 to the power 10, and that is 2.25 into 10 to the power 20, right? So now, am I audible? Am I audible? Please type that in the chat. Is my voice audible?
Yes, sir.
Thank you. So in equilibrium, your N naught P naught is N square, right? And whenever your excess carriers are present, NP is not equal to Ni square. Here excess carriers were as a result of optical generation process. Okay, and the amount of deviation, how much this NP deviates from Ni square, that quantifies departure from the equilibrium. Okay, so how far have we departed from the equilibrium? The more the difference, the more the departure from the equilibrium. The less the difference means that we are very near to the equilibrium. And what about our current system? Your Ni square is this, and your NP is this. So there, the difference is considerable, right? So we have departed considerably from the equilibrium in our present case or system, whatever, right? Now let's move on to the third question. So I need to determine the locations of EFN and EFP and compare their locations with the equilibrium Fermi level EF, right? This is the third question. I need to compute the locations of quasi-Fermi levels EFN and EFP, and I need to compare their locations with the equilibrium Fermi level EF, right? And what is the position of the equilibrium Fermi level? Let's talk with reference to intrinsic Fermi level EI. So what is EI minus EF? Should use a look. What is EI minus EF? You are supposed to know these formulas. I also taught or wrote this in the last session. So this is KT by ln of P naught by Ni, right? Or you can equivalently write it in terms of N naught. I'll assume you can do that on your own. So that is 0.026 times ln of this is 10 to the power 15 whole divided by 1.5 into 10 to the power 10, right? And this is equal to 0.289 electron volt, correct? So your Fermi level is below EI, right? Since EI minus CF is a positive quantity. So now in the presence of the excess carriers, so this was the case when we were talking about the equilibrium. Now excess carrier case, right? When we are having excess carriers, the position of the electron quasi-Fermi level, right? EFN. Right. What is EFN minus CI? KT. Okay, first, what is this? EF minus CI. Because only then you would able to compute this. What is this? This is KT ln of N by Ni. N naught, sorry. And in this case, your N naught would be replaced with the overall electron concentration, right? This would be ln of N by Ni. Right, and if you plug in the numbers, which I'll leave as an exercise for you, use this N, right? And Ni you know, right? Ni you know, Ni is this. You'll get this number. EFN minus CFI is 0.151 electron volt. And what is the position of the whole quasi-Fermi level? That would be EI minus EFP, right? Which would be equal to KT ln of E by Ni, which would be equal to 0.289 electron volt. Okay, so now you have all the three locations, right? The location of the equilibrium Fermi level, the electron quasi-Fermi level, and whole quasi-Fermi level, right? Now, uh, let's make a band diagram for this case. So this is your EC, right? This your EV. What is this? This is EI, right? This is your EFN, right? What is this? EFP, right? 0.289 electron volt, right? What about this? This is your 0.151 electron volt, right? And if you'll notice, these two are roughly same, right? So this is approximately a equilibrium formula. Okay, so that finishes this question. Yeah, so we can probably move on to the next one now. So an intrinsic silicon sample. Okay, so we have this. Okay, so an intrinsic silicon sample is doped with a position-dependent acceptor concentration Ne of x as N naught 1 plus x by L, as shown in the figure. I guess I did not show you the figure. I'll do that. Just a second. So this is your P of x. Sorry, Ne of x. Okay. Fine, this is your P of X. And it's equal to N naught X equals to 0. And it's equal to, say, a value, some value at it, like this. Now, let's come to the question back. So your NE of X is equal to your N naught 1 plus X by L, right? Your N naught is equal to 10 to the power 15 per centimeter cube, and L is equal to 5 micrometer, right? Now, what is the equilibrium hole current density? JP? See, I need an expression for E of X, right? And to compute that, I'll use the fact that the hole current density at equilibrium is 0, right? So that's why I'm saying what is hole current density? This is equal to Q mu P, P of X, E of X, right? The drift current density part. And then you have a minus sign, right? Since it's hole current density. These are diffusion. This is the diffusion part, right? This is equal to Q dP, dP of X by dx, right? And you need to equate this to 0. Why? Because you're talking about equilibrium. That's why. So your E of X would be equal to, do the calculation, this would be dP by mu P, 1 by P of X, and then you have dP of X by dx, right? And since your dP by mu P, what is dP by mu P equal to from Einstein's relation? Remember?
KT by
Einstein's
Q.
KT by Q. So if we use that and wait, we can do a few things. So this would give you that your P of X is equal to N naught 1 plus X by L, right? What about now this d by dx of P of X? What is that equal to? Agree? This would be N naught by L from this. First term would have a 0 as a derivative. For the second term, your second term is N naught X by L. If you differentiate this with respect to X, you'll have N naught by L. That's what I wrote. Okay, I guess it's clear. So this is equal to N naught by L. What is this? This is this, right? N naught 1 plus X by L. Let me write, otherwise this would be a little too fast. So dP by mu P is KT by Q, 1 by P. So this is your N naught 1 plus X by L times dP by mu, dP by dx, right? And dP by dx is N naught by L. This and this can go. We'll be left with E of x, and that is equal to done. I'll take that as a yes. So we computed the expression for electric field at equilibrium, right? So now we are asked in the second part, we are asked to evaluate it at x equal to 0 and x equal to 5 micrometer. Okay, so that is just a numerical problem more than a physical problem. So for your B part, what is E of 0? E of 0 would be KT by QL, right? Why? Because I substituted x equal to 0 in this expression that we just derived. What about E of L? Why I'm writing E of L? Because my L is 5 micrometer, right? So we are asked to calculate E of x at L, at this edge point. What is E of L? Your E of L is KT by 2QL. Okay, so just check it. This one is this one is 52 volt per centimeter, and this one is half of that, 26 volt per centimeter. You'll just plug in the numbers and verify it on your own. Now part C. In part C, you need to sketch the qualitatively correct band diagram, and you need to indicate the direction of V of x for the given etc distribution. So firstly, we need to uh, obtain the dependence, right? How should your electric field vary with x? See, we know that, sorry, I just uh, said the other thing. See, we know that electric field varies inversely with x. So how should our band diagram vary with x? We know this relation, right? That your electric field is equal to your 1 over q dei by dx, right? And so there is a quantity whose, when derivative is taken, would result in an inverse variation with x, which is that mathematical dependence. This would be how should E of I vary with x? What should be I of x? Such that E of x is 1 over x dependent. In other words, I'm asking for a function whose, when derivative is taken, you obtain 1 over x. Log, right? Natural logarithm. So your E of I and consequently both your EC and EV as well, right? They will have logarithmic dependence on x, right? So we have following. This is your 0. This is your L. This is EV. This is EC. And this is EI. Right? And this dependence that I just drew is natural logarithmic dependence. Okay, so this finishes your this question. What about this? Compute the value of dn by mu n if your T is equal to 400 Kelvin. Again, you'll use Einstein relation, right? And from Einstein's relation, your dn by mu n is kT by q, right? You know that at room temperature, your kT by q value is 26 millivolts, right? Now, you need to compute kT by q at T equal to 400 Kelvin. That is effectively the question. I'll leave this as an exercise for you. Right, this would be slightly greater than 26 millivolts, right? Because uh, T is a numerator. So if at 300 Kelvin you're getting 26 millivolts, at 400 Kelvin you'll get a quantity that is slightly greater than 26 millivolts. So this finishes question 5. And uh, after that, I'll leave uh, homework for you. You'll do one thing, you'll solve relevant problems from uh, Semiconductor Device Fundamentals by Robert Parrott. Okay. Whatever content is taught by the instructor, you'll find the relevant solved and unsolved problems on Robert Parrott and then proceed to solve them. And if you have any question, you can mail me the doubt regarding those problems. Is it fine? And also compute this. Do let me know what is the answer in the next session. Does anyone have any specific query or would like to discuss anything else? Because we wrapped the session. So if I'll have very few students, that would make it very easy for me because the sessions won't last longer than 1 hour. Unless I'll have 10 to 20 students, then probably we'll have, longer sessions. Good for me. Does anyone have any doubt? Pranav, any doubt?
No, sir.
No?
No,
So,
not also.
okay, thank you. So, I guess that's all from my side then. We'll end this meeting then. Thanks to those students who tuned in for this live session. Thank you. Thank you.
Thank you, sir.